Okay, this video is Why Are Diabetics So Stupid Part 2. I've already previously made a video about why are diabetics so stupid. This is Part 2, Why Diabetics Are So Stupid, and this is really interesting stuff. Okay, so first of all, brief review of the plasma membrane function. There is a sodium-potassium ATP pump. This is about 25% to 1/3 of the energy used by the entire cell goes to this pump in a regular cell. In a brain cell, it's 50% to 2/3. So let's just call it 2/3. That's a lot. And you can remember that by the gradient is about 2/3 as well, negative 65 millivolts. So this pump pumps out sodium, and that it causes a concentration gradient because you're pumping out a lot of sodium here. So you got 10 times as much sodium outside the cell than inside the cell. That makes sodium want to very much get into the cell to equalize its gradient. It's also attracted to the negative charge inside the cell because when you pump out all that positive charge, you have a net negative charge across the plasma membrane. That eager desire of sodium, which I call the angry poor to break into the city, is used to couple the pumping of other things. So here, sodium is pumped out at the plasma membrane, ATPase, sodium, potassium, ATPase. Everywhere else, sodium is brought into the cell, coupled to the transport of something else. Okay, and so of course you need it to pump the calcium out. We've talked about that before. But it's also used to pump out hydrogen ions, protons. Okay, H plus is a proton. All right, now this is going to get really interesting. We talked also about how when you have elevated insulin levels, you end up running more glycolysis. There's another mechanism that I don't fully understand yet, but the net result is when there's higher insulin levels in the blood, it leads to higher amount of protons being produced in the cell cytoplasm, and then the cell must pump those out, which it does. And it actually upregulates, makes more of these membrane pumps to pump more protons into the extracellular space. That's going to make the extracellular space acidic. I know some of this you might have seen before, but I can guarantee you, you have not seen what's coming. Okay, now here's something new for you. Now, the protons being pumped into the extracellular space, they acidify the extracellular space. So this means increased pH. Oh shoot, that should be decreased pH of the extracellular space. I got to fix that. Okay, well anyways, it causes inhibition of the insulin receptor, and it lowers its binding affinity for the receptor, so it causes more insulin resistance. And you get a little bit of a vicious cycle. But the reason I'm showing you the slide, what's interesting about this slide? And what's interesting about the slide is that when there starts being problems with glucose metabolism, the cell can switch to primarily metabolizing glutamine. That's very interesting because that's like what a cancer cell could do. And that's one of the points I'm trying to make here. I wrote déjà vu, is that a cancer cell metabolism and diabetes metabolism have a lots and lots of overlap. Basically, diabetes cell metabolism is very much like the beginning of cancer cell metabolism. Cancer is just taking it farther. But you're seeing all kinds of changes. A change to more and more anaerobic metabolism. The high-fat diet is causing blood sludge and tissue hypoxia. Hypoxia activating the hypoxia-inducible factor and VEGF, vascular endothelial growth factor pathways. So what I'm trying to say here is, just like high-fat diets push towards diabetes, they also push towards tissue hypoxia, and they also push towards a form of metabolism that seems very similar to cancer. Okay, so that's important. The reason they sound similar is because they are similar. All right, so here's a little bit about ion pumps for protons. You have N is for natrium, for sodium. That's the Latin word for sodium, natrium. H is just for hydrogen. E is for exchanger. So you'll see it abbreviated NHE. That's the sodium hydrogen exchanger. And that is the primary pump to pump these protons out of the cytoplasm into the extracellular space, thus lowering the pH of the extracellular space. Okay, there's some other pumps. We'll talk about those in a moment. Now here's a completely new article for you. Diabetes mellitus, DM, is associated with decreased pH in the extracellular space. Insulin levels are increased, and when they're increased, they're associated with decreased pH in the extracellular space. I just went over all of that. And the reason for that, you don't see a big change in the blood pH is because the blood has strong pH buffer systems. It's got the bicarbonate CO2 system. It's got hemoglobin related to buffering. Hydrogen protons can bind to hemoglobin. The hydrogen protons can bind to albumin. And all of that is very good at keeping the pH of the blood tightly regulated between 7.35 and 7.45. However, the extracellular space is also called the interstitial fluid. It has very little pH buffering capacity. Therefore, its pH can vary a lot. The reason why the pH is so variable in the extracellular space is because it can't really have that many proteins or other things in it with osmotic ability, because if it did, you wouldn't be able to get the waste products of the cells back into the capillaries. If the oncotic osmotic pressure was too high in the extracellular space, the blood would have no way at the distal end, the venous end of the capillary, of pulling things into it. So it just doesn't have much pH buffering capacity. Okay, and the extracellular space in diabetics has a much lower pH than in normal control patients. They've also seen, if you take metabolic syndrome patients, sort of like prediabetes, diabetes, and you check their urine pH, they will also have a low pH because they're excreting more protons in there. This author's name is Maronaka, and this is a great paper, by the way. Role of interstitial fluid pH in diabetes. Okay. What are some other interesting things? Oh, and what we're going to talk about is that extracellular space is in continuity with synapses. So something in the interstitial space, extracellular space, means it's also going to affect the synaptic cleft. And that's how this is going to relate to a mechanism for cognitive decline in diabetes. Because, hormones like insulin and neurotransmitters like glutamate, they have to bind their receptor in the extracellular space. And if you have extracellular space decreased pH, meaning it's acidification of the extracellular space, that can cause a change in the binding affinity of insulin to the insulin receptor. We talked about that. But it'll also cause a change in the binding affinity of some neurotransmitters for their neurotransmitter receptor. And that's a big deal. Okay, this is more of the same about how the blood has a very good pH buffer, but the interstitial space. Interstitial space is the space around the cell. So you're outside of the blood vessels, you're just in the space in between cells. That's the interstitial space. Okay. And we know that diabetes is associated with mitochondrial dysfunction. So that's another reason why these cells will run more anaerobic glycolysis. A cancer also runs more anaerobic glycolysis. How interesting. Okay. Ketone bodies also lead to increased production of acid in the extracellular space. Okay, so one point I want to make is here's lactic acid, and at physiologic pH it's deprotonated. So a deprotonated version of a carboxylic acid, like lactic acid, it becomes lactate. So there's a deprotonated, meaning the hydrogen is absent. Okay. I'm going to show you a little bit about how the hydrogen protons are handled. So the cell runs more glycolysis. The glycolysis leads to the production of lactate plus H+. And when you're running a lot of anaerobic glycolysis, you produce a lot of H+ from this. So some of the H+ goes to here, the NHE, that's the sodium hydrogen exchanger, and that'll pump H+ into the interstitial space. Okay. There's also just a pure ATP-driven H+ pump. That'll pump some out. And there's the MCT, the monocarboxylate acid transporter. I call it the MCAT, even though it's most commonly called the MCT. All right, and that simultaneously will pump out lactate and the H+. Okay, and that also pump out ketone bodies. All right, so anyways, all this H+ from the interstitial space, it'll go to the blood. It can bind to albumin, for example. Okay, the mitochondria, to the extent that it's working, can also blow off CO2. The CO2 goes into the red blood cells. It can go through the bicarbonate buffer. We're not going to get into all that too much, but the CO2 then can be exhaled in the lungs. We want to know that. We talked about protons can also be excreted in the kidneys. Okay, I'm just showing you a slide to get a sense of what's involved here, but the bottom line is the cell upregulates these proton pumps to get the protons out of the cytoplasm, and it does that because if the pH went too low in the cytoplasm, it would start to damage all the enzymes and destroy the cell, kill the cell. In the papers, you'll hear lactic acid described as an organic acid. It's got carbon in it. Okay, that's an organic acid in that sense. It's got carbon. Okay. Well, I didn't get into these other pumps, so I don't think we need to, but just be aware the bicarbonate system contributes with regard to CO2. Now, here's the main point of this whole talk. The fact that we just talked about how in cells, when there's insulin resistance, quite often due to, of course, mitochondrial dysfunction, because the mitochondria is not working well, it can't make that much ATP. So the cell compensates by running glycolysis in the cytoplasm, anaerobic glycolysis. That generates a lot of protons, lactate plus H plus. And then the H plus is pumped out into the extracellular space, also called the interstitial space, interstitial fluid, and that is in continuity with the synaptic cleft between the presynaptic neuron and the postsynaptic neuron. So there's neuron number 1, neuron number 2. To send it a message, the cell would release its neurotransmitters. They'll diffuse across the synaptic cleft, and on the other side of the postsynaptic neuron, the neurotransmitter, this little black circle, will bind this receptor in the plasma membrane of the postsynaptic neuron. And what I'm saying here is because you have acidification of the extracellular space, too many protons in there, that can disrupt the binding affinity of the neurotransmitter and thus cause decreased cognitive function because you can't effectively send messages when your neurotransmitter is not normally binding to its receptor on the postsynaptic neuron. And that can cause cognitive decline. So this is another problem in diabetics. I've previously given lectures about why diabetics are so stupid. And I'm telling them this, and this is why if you've got diabetes, you don't want to be sitting around saying it's under control with medications. You want to fix your diet as fast as you can so you don't run into these problems. And if you have, complete loss of your pancreas beta cell function, then you want to eat the healthy diet so you minimize insulin resistance and you minimize all these problems. Because I know some diabetics who are really smart. Look at that guy, Michael Brownlee, the genius who wrote that paper, Unifying Theory of Diabetes Complications. Okay, he's a type 1 diabetic. Okay, look at that Bobby Bitterow. I guess it's Robbie Barbaro from Mastering Diabetes. He's a very smart guy. He gave a great review of his causes of insulin resistance. So Dr. McDougall and Bobby Barbaro have both given great reviews of insulin resistance. McDougall's the one who kept all that information alive. A lot of that would have been forgotten if it wasn't for Dr. McDougall. But what I'm trying to tell you is I'm going in another direction here. Everything that Dr. McDougall and Bobby Barbaro have said is true. I've been impressed by their summaries of the material, but I'm taking you into new material about diabetes that I think is rather fascinating. And hopefully this will motivate a patient that basically if they don't get their act together, they're headed for brain damage, okay? So there's pretty good motivation there. I think that's my last slide here. Yes. So anyways, I hope you found that interesting, the idea that excess of anaerobic glycolysis, which a cell does because its mitochondria are not working, because you have mitochondrial dysfunction as the main mechanism of insulin resistance, leads to lots of protons being made at the end product of glycolysis with lactate plus H plus. That H plus gets pumped into the extracellular space, and it lowers the pH, makes it acidic. More protons means more acid. And that high acidity of the extracellular space, in continuity with the synaptic cleft, which is also part of the extracellular space, will sometimes decrease the binding affinity of neurotransmitters and cause neuronal dysfunction, leading to cognitive decline. So it's good to know that happens so you know what you can do to minimize it. And some diabetics have maintained themselves really, really smart, at least into their 60s, I think into their 70s.